So let's talk about proof. So section 3.2 is sort of extending the previous notes. We're going to talk about how to prove some of the statements that we've already made. So our goals for the lesson, we're going to define what a geometric proof is and how two-column proof relates to a flow proof. We're going to discuss what information you can pull from a diagram, and then we're going to prove alternate interior angles are congruent, alternate exterior angles are congruent, and if we have time, we're going to talk about the consecutive angle theorems. So let's start with the alternate interior angles theorem. There are four essential parts for a geometric proof. The first thing is a diagram of the statement that you're trying to prove. That diagram gives you specific points, specific lines to discuss in your proof. You have a given statement, which is specific to the diagram. The given is the hypothesis of an if-then statement. The proof statement is the conclusion. Specific to the diagram, it's the conclusion of the if-then. And then finally, the actual proof itself. You're using the laws of deductive reasoning, the laws of logic to build an argument for your proof statement. And then we'll talk a little bit about some ways to spice up a proof, let's say. All right. So we have these three main types, two-column proof, flow proof, and paragraph proof. We're going to spend most of the time talking about flow proof. So what is a flow proof? A flow proof is essentially a picture, a diagram of the law of detachment. Remember, the law of detachment says, if P then Q is a true statement, and then we learn that P is true, we determine, therefore, Q is true. In a flow proof, what this is going to look like is we have a box with the statement P is true. In other words, we satisfy the if part of the sentence. That allows us to conclude that Q is true. Why? Well, we know that if P, then Q. So this flow chart, right, the arrow from box to box, must have some type of if-then statement or property or some type of reason why P implies Q. So some given information based on the diagram that you are allowed to kind of pull as not as a freebie, but just essentially the way the diagram is drawn. We might have a shared side. So for example, here we have two triangles, and they both share the side AB. We'll talk a little bit more about that in upcoming chapters. Vertical angle pairs. Whenever you have two lines intersecting, it doesn't have to be triangles like this, but whenever you have two lines that intersect, then the vertical angle pair that exists, or the vertical angle pairs that exist, would be congruent. Next, a shared angle. When you look at this diagram, you could look at one triangle cut by segment HR, or consider two overlapping triangles. The big one, triangle AES, and then the smaller one, ARH. Both big and small triangles share angle A, and so that would be considered congruent in both triangles. And again, we'll talk more about this stuff as we go on. And then lastly, a linear pair. If you ever see two angles that form opposite rays, then we can call those linear pairs, and so we get that that's supplementary information. So we're going to begin with one postulate. A postulate is a statement that suggests or assumes the existence, fact, or truth of something as the basis for reasoning, discussion, or belief. In other words, we're going to use one postulate as our premise. And from that, we're going to build all these other statements. So our postulate, if two parallel lines are cut by a transversal, then each pair of corresponding angles is congruent. We're going to assume that this is true. We're not going to prove it, but we're going to assume it. And if we assume that, what else can we get? So once again, this corresponding angles postulate would say, well, for sake of any argument, we could say, pick these two angles. We know if the lines are parallel and cut by a transversal, then corresponding angles must be congruent. All right, we're ready for our first proof. we are going to prove that alternate interior angles are congruent based on the previous information, based on corresponding angles. So we want to prove if two parallel lines are cut by a transversal, then each pair of alternate interior angles is congruent. Or to put it shortly, if parallel lines, then alternate interior angles are congruent. Remember, for any proof, you want to start with a diagram. So the hypothesis says if two parallel lines are cut by a transversal. So we need two parallel lines cut by a transversal. Let's call them M and N, cut by line T. Our goal is to prove that each pair of alternate interior angles is congruent. So for example, these two angles, we would have to prove that they're congruent. By the same logic, we could prove that the green angles are congruent. And so to streamline this, we're just going to look at the red angles. Now note that whenever we have two lines that intersect, like M and T, N and T, we create vertical angles. So for example, the two red angles at the top would be considered congruent. They're vertical angles. And likewise down here. Basically, we've got a bunch of vertical angles as well as some other angle relationships. Also note that these two angles would be considered corresponding angles. And again, there are three other corresponding angle pairs, but let's just look at those. In fact, let's just look at these three angles. We have our corresponding angles, we have our vertical angles, and those angles will allow us to prove that our alternate interiors are congruent. In other words, we know 1 and 3 are congruent because they're corresponding. We know 1 and 2 are congruent because they're vertical. Okay, so given information, based on the diagram, we're given that M is parallel to N and cut by transversal T. And our goal is to prove that angle 2 is congruent to angle 3. Because by the same logic, if we can prove that one pair of alternate interior angles are congruent, then the other pair is congruent as well. Alright, so let's begin our proof. From our postulate, we know that 1 and 3 are congruent. Why? M and N are parallel lines, and our postulate says if I have parallel lines, then corresponding angles must be congruent. Next, we know that 1 is congruent to 2. Why? Well, because 1 and 2 are vertical angles, and vertical angles exist whenever we have lines that intersect. We know we have M and N parallel and cut by T. In other words, T intersects both M and N, which create vertical angles, and vertical angles, if they exist, then those vertical angles are congruent. That was one of those, I guess, kind of those given information, not quite given, but one of the things that you can pull from the diagram. And so if 1 equals 3 and 1 equals 2, then 2 must equal 3. The statement that guarantees that is called the transitive property of equality. And I'm not expecting you to know that right now, but as we move throughout this chapter, you will. And then we're done. QED. You asked me to show that 2 is congruent to 3, and I did it. Lastly, we can add a statement of sort of more general fact. Since 2 is congruent to 3, we know that if two parallel lines are cut by a transversal, then each pair of alternate interior angles would be congruent. We proved this for angles 2 and 3. By the same logic, the same argument would prove that the other pair of alternate interior angles was congruent. So how does this proof compare with a 2-column proof? So here's a 2-column proof of the same. We'd have a statement followed by its reason. We know M was parallel to N because it was given. 1 is congruent to 3 because if we had parallel lines, then corresponding angles was congruent. 1 was congruent to 2 because we had vertical angles, and if they're vertical angles, then those angles are congruent. And then using the transitive property from statements 2 and 3, we know that angles 2 and 3 are congruent. So again, 2 ways to write the same proof. For this next proof, we want to now prove that alternate exterior angles are congruent. In other words, we want to prove that these two angles are congruent to each other. Well, we're going to follow actually a similar tack, a similar line of logic. We're going to use these corresponding angles and vertical angles to prove this. So, given that M and N are parallel with transversal T, we want to prove that 7 is congruent to 9. So we know 7 is congruent to 8. Why? Because lines M and N are parallel, and our original postulate stated if we had two parallel lines, then corresponding angles were congruent. We also knew that angle 8 was congruent to angle 9. Why? Well, those are vertical angles. And vertical angles exist whenever you have lines that intersect, just like N intersects with T. And so therefore, if those vertical angles exist, then the vertical angles are congruent. And so if 7 equals 8 and 8 equals 9, we know by the transitive property that 7 is equal to 9. And therefore we've proven that if two parallel lines are cut by a transversal, then each pair of alternate exterior angles is congruent. That was a lot to write down. Good job.